Alright, so the last part of this one is eigenvectors and eigenspaces. Again, something we've already done. We're just going to call it the process what it is, especially the eigenspace itself. Okay, but just for a little quick review, let's go back to finding eigenvalues and eigenvectors of this associative property. So we already did this earlier in the past videos, so we know that lambda is equal to these three numbers here. So now we're just going to find the eigenvectors associated for each one. Okay? So we start with the first one, and lambda is equal to -1. So therefore, I'm just going to be, in this case, subtracting or addition these three. So add 1, and add 1 straight down. And now we just straight row reduction itself. So if it's easier, I do this minus this, and then get rid of the 12 by multiplying by 3 and canceling stuff out. And eventually get something along of this. And if I divide this by 5, notice it will eventually just cancel out if I just add these together. So if I just rearrange this a little bit, put this on top, and then I'll leave this one here. Gives me that. Alright, so therefore, this is going to equal to 4x1 is equal to 2x2, and x2 is equal to x3. So if I just rewrite these with this proper format, I'm going to have 4, well, I'll just divide it over. x1 is actually equal to 1/2 x3 because these are the same, and x2 is equal to x3, and x3 is arbitrary. So the vector would be some value a with these processes as 1/2, 1, and 1. Okay, and then we do the same thing for the other two. So if lambda is equal to 1 in this case, well, now we actually would subtract. And we do the same process. So slowly breaking it down, and again I eventually get something along of this. So this gives me -14x1 equals 6x3, and -7x2 equals x3. Okay. Oh, negative, sorry. Negative. So you'll notice the same process happens. They're all associated with x3. So some arbitrary value a, which represents x3, is equal to divide over, so 14 over 6, or 7/3. Positive, divide this over, so -1/7, and then 1 represents the x3. So there's my eigenvector for this situation. And then lastly, we do the 2. So minusing 2 everywhere. Gives us that. And again, slowly breaking this stuff down, and I eventually get this. All right, so notice it's the same process we have here. So 2x1 is equal to x3, and 2x2 is equal to minus x3. Okay. All right, so some arbitrary value divided over, so 1/2, negative 1/2, and 1. Or if you want, all right, alternative is if you want to get rid of all the fractions, just multiply this by 2. So 2, so 1, 2, 2. Multiply this by 21, I guess if you want to call it, it's just scalar. And multiply this by 2, so an alternative would be 1, negative 1, 2 as well. Okay. All right, so a little review of just eigenvectors themselves. All right, so now I get into the goal of it is what is an eigenspace? Now the good thing is we've already done this. Now we're just going to actually give it a name. So let A be the n by n matrix. If lambda is an eigenvalue of A, then the null space of A minus lambda I, so the null space of this determinant, denoted as E sub lambda, is called the eigenspace of lambda. Okay. The dimension of the eigenspace is called the geometric multiplicity of lambda. Okay. So why don't we do a couple examples illustrating this itself. So for all of these matrices, we're going to find the algebraic and geometric for the eigenvalues, and I'm also going to define the eigenspace so you can see how that's going to go about doing it as well. Okay. All right, so first, polynomial, and this one's kind of nice. Again, these are all triangular matrices, so it's just straight this. So which is even better because we only have one eigenvalue. Okay. So if we plug it in, so we're subtracting all these ones, so it'll be 0, 1, 0, 0, 0, 1, 0, 0, 0. We're pretty much done. So this is saying x3 is any, but x1 and x2 have to equal 0. Okay. So an arbitrary value A is getting equal to, well, x3 could be anything I want. Oh, I'm sorry. X1 could be anything I want. X1 could be, so this is x2, x3, right? 2 and 3, yeah, there you go. So x1 could be anything I want, so I'll just pick 1, 0, 0. Right, technically this is our A1 value there. So what does this mean? So if I go back, so that means the eigenspace of this portion will just be all the vectors combined, so it's just going to be the vector 1, 0, 0, or A, or x1, 0, 0, or 1, 0, 0. So the geometric is just 1, because there's only one vector involved. The algebraic represents as the power of that individual, and the power here is going to be 3. And that's how we find them. Okay. It's quantum B. So same thing, it's already diagonal, so it's going to be the same portion, so we get only 1. Therefore, algebraic again is still going to be 3. Again, we subtract them. We have this. So again, what it's saying, this is saying x2 equals 0, and x1 and x3 is any real number I want it to be. So again, now this could be a bit tricky because now we have two different independent variables. Okay, and remember, when we talk about bases in null space, right? Null space is a subspace. So we want to break it down and actually into individual vectors themselves. The question is, how do we write this in vector format? Okay, so we have an arbitrary, well, start from the beginning. So let's just go from each one. So we have x1. Well, no matter what, x2 has to be 0. This is x1, and that's 0 because it has 0 x3, so it has nothing to do with it. Plus x3. Again, x2 has to be 0. This must be 0. This must be 1. Because again, if I multiply these up and add them together, I get an arbitrary values, right? It's just x1 plus x3 because they're independent of each other. So this is actually my Eigenspace for lambda equaling 1. So this time our geometric approach, or our geometric multiplier, is 2. 1, 2. Now we'll do the same thing for the last one. So now if I subtract by 1, notice we get all 3 being independent variables. So if we follow the same template here, we have 3 independent variables. We have x1, x2, and x3. Well, x1 must be 1, 0, 0, because it goes away. x2 must be 0, 1, 0, and x3 is 0, 0, 1. So this right here is the space, the subspace. With geometric of 3. All right, so why is this important? Why do we care about the geometric and the algebraic? It's because, well, we have a nice little definition summarizing that. So this is saying that A being an n by n matrix, if the eigenvalue of lambda is of A such that the geometric multiplier of A is less than the algebraic multiplier of lambda, then it's called a defective matrix. And there we go. We won't get too crazy about what defective matrix are, but actually pretty powerful stuff and useful stuff, and as you go along into matrices or linear algebra. But what it's saying is, what it really means is, if we have an n by n matrix A, and we have n linear independent eigenvectors or not, by this definition, if the matrix is defective, then the matrix A does not have linear independent eigenvectors. That's the key thing. Again, going forward, is if it's defective, that's the key thing, then we do not have n linear independent eigenvectors, because we were promised that earlier to do so. So this is a nice little check to show if that actually works or not. So here's an example. So find all, just like the last one, find all the vectors and values of the matrix, and then find the algebraic and geometric multiplier for each eigenvalues. Okay. All right, so 4 by 4, horrible mess. So again, skip the initial step, and this is going to be the polynomial. So we have 2 eigenvalues, 1 and 2. So for this process, we just follow right. We would just subtract diagonals minus 2, or minus 1 actually. So we get this matrix. Now again, eventually, a little bit of work. This breaks down to these type of situations. We have x1 equaling and x2 equaling this. Or again, x3 and x4 are in any values. So this one we had an algebraic of 1, or actually not 1, 3. We got 3 here. Algebraic of 3. And breaking this down, again, using its independent variables, right? This is the same thing as writing like this. So x3 would be taken out of here, so it would be 1/3. And here it would be negative 2/3, 1 and 0. Same process here. This would be 1/3, 2/3, 0 and 1. And there is our eigenspace for lambda equaling 1, which geometric multiplier is equal to 2, 1, 2. Yep. So we do the same thing for 2. So this time it has an algebraic of 1. There's only 1 power. Minus 2. There we go. Okay, and again, slowly break this down, and I eventually got this. Yep. Now again, notice they all depend on one vector, so that's going to be just x4. So 3/5, 8/5, 1 and 0, or 1 and 1 actually, since x equals that. And there we go. So this has geometric of 1. So therefore, let's go back to this theorem about defectiveness. So we have to check both conditions because it works here, 1 to 1, right? So we probably say it's not defective, but this is where it fails. So it has to follow all eigenvalues, right? Because this is an arbitrary eigenvalue in the definition. So you have to treat it as an all arbitrary value. So if you want to go one more step further, you would say this is a defective matrix. Okay. All right. Last theorem and last example is connecting the two dots. So the two major things that we talked about in way back in the day is linear independency, and now it shows using matrix format of what a linear independency represents itself. Okay. So let U's through K's be eigenvectors of an n by n matrix corresponding to distinct eigenvalues. So therefore, A times the set of vectors is equal to lambda times the set of vectors, which makes sense because it's lambda itself. But this is the key thing. The set of vectors is actually linear independent. Okay. So what does that mean? So let A be an n by n matrix. If A has n distinct eigenvalues, then A has a set of n linear independent eigenvectors. So this distinct is a key thing, means there's no repeats. So if we find eigenvalues that are non-repetitive, therefore we know that the eigenvectors themselves, once we find them, is also a linear independent, meaning function-wise, right? We do all that fun stuff because of linear independency. So last example is a little fun one. It's a little bit of a proof to show one way to what you can do with these theorems. So let n be an n by n matrix P, called idempotent if p squared is equal to A. Show that if P is invertible idempotent matrix, then P equals I. Okay. So what are we given? We're given this, and we're also given invertible. Okay, so what does invertible mean? So that means we have an inverse. So I'm going to force the inverse to be true. I'm going to say that P inverse, this right here, is its inverse of P. Right, it doesn't have to be, but I'm assuming it is. Okay, so let's just start there, because we have an equation. Okay. All right, so we have that, and we have this happening as well. So we also have P squared is equal to P. Now, we talked about this earlier, right? It's technically not squared, but in general, we can write it as P dot P, and it still doesn't break the dot product. Okay. All right, well, I wanted to show that P equals I somehow. So we got to use the fact that this is true. I'm going to multiply both sides by P inverse. So on the left side. Okay. Now, according to our formula, when you multiply its inverse times the original, you get I. And look what we have here. Those are in opposites, so this ends up being just I. Okay. Well, the identity matrix times any other matrix will give you itself back. So on this side, we just left with P. And on the other side, again, we just showed that's true. All right, donezo.